So there are two curves on top of each other, and when this figure popped out on my computer screen, I went like this, and I was really excited. The reason was green curve. I got this. I'm gonna tell you what's plotted here. It's the inverse localization length. The green curve is the what I obtained back in 1996, and at that time I was pretty sure about the validity of this curve, but I didn't confirm by other methods of numerical calculations. And this year, I found a new method to compute this inverse localization length, and they fall on top of each other. So that's what I'm talking about. So I'm going to talk about this non-Hermitian Anderson model first, and then I'm going to talk about this Chebyshev polynomial expansion in the second half of my talk. Okay, so now I'm going to talk about this inverse localization length. It's all about the Anderson localization. Anderson localization is first, the concept of Anderson localization is first developed by Phil Anderson. It's, well, it's originally for quantum mechanics, but it's about all wave expansion. So suppose you have some kind of wave media, and you have many impurities like this. And suppose you throw a stone on here, and then you have a wave expanding, but then because of these impurities, you have many other waves, and under some condition, these all waves, because they are randomly overlapped, under some condition, they work disruptively each other, and because of that, this wave cannot go propagate far away. So that's called Anderson localization. And originally, as I said, it was the idea was proposed for explaining the metal insulator transition in electron materials. So if you have a density of states like this versus the energy, and in 3 dimensions, it's said that there was a critical energy, which is called mobility edge, below which its states are localized, and above which states are extended. So if the material has a Fermi energy up here, then these parts of the electrons can be mobilized, and it's going to be metal. While if the electrons only up to here, then because all states here are localized, it's going to be an insulator. So that's the idea of Anderson localization in 3 dimensions. But in 1 dimension, because there are not many paths going around the impurities, in fact, you have to go straight in 1 dimension, obviously. So almost all waves walk on destructively. And because of that, almost all states, in fact, all states except the very, very exceptional cases are localized in 1 dimension. And by localized, I mean that the shape is this kind, exponentially decaying around the localization center. And so the localization length scale is kappa inverse. Kappa is here. And so this is the localization length scale. So we call this kappa as inverse localization length. In 1 dimension, it's sometimes called Lyapunov exponent, but I don't use that word for now. So this is an inverse localization length, and typically kappa is small for higher energy, and kappa is large for lower energy, because for higher energy the localization is weak, so which means that the wave function is wide enough, and so it has a long localization length, and because kappa is inverse localization length, kappa is small. So kappa is small for higher energy, and kappa is large for lower energy, typically. But what I'm going to talk about now is mostly about what this one-dimensional tight binding model. And in the tight binding model, the situation is a little bit different. So let me also talk about that. So here's the tight binding models. So this is the hopping term. It means that the particle at the site X hops into the next right side with this amplitude, and it can move back from this side to the left neighbor by the same hopping amplitude. And this is the random potential part. So potential is random here. So all states are actually localized in this, and the energy dependence of the inverse localization length looks like this. So that's what I'm going to show you. So for here, indeed, if energy is low, for lower energy, kappa is large, and for higher energy, kappa is small. But because it's a tight binding model and the energy is bounded from above 2, if you go to an even higher energy, again, the localization becomes stronger and kappa becomes larger. Okay, so this is the basic behavior of the inverse localization length for a tight binding model, and with random potential. Okay, and I'm going to show you how I computed these curves, but typically, if you don't use those methods I found, typically what you could do is this transfer matrix method. So this is the Schrödinger equation of that Hamiltonian, and you can map this into this kind of transfer matrix. So this times this gives this, and this times this gives a trivial equation. So this is transfer matrix. This gives the right wave function amplitude from the left neighbor, right? And then you set some initial condition and compute this the right wave function component, and typically it looks like this. Because of this randomness, it goes up and down. And if it decays enough, and at least numerically, it's really noisy here, down here. So then you are going to have to, you first have to, because this is an initial relaxation, you want to remove this, and also because this is noise, you want to remove this. And so you are sort of choosing carefully in the mid region and numerically do fit. But I really don't like the numerical fitting of numerical data. It's really a nasty job. So I really don't like this method. So now I'm going to talk about the first method, which I found in 96, and that's about making that 1D tight binding model non-Hermitian. Okay, so the non-Hermitian coefficient is introduced in this way. So because I choose G as a real parameter, so this is obviously this is non-Hermitian. So this right-going amplitude is greater than left-going amplitude. So there is a direction into this direction, preference to the right. Okay. Say it again.
G is real.
G is real. Yes, G is real. Say it again.
What is the motivation for this model?
It's going to take me 10 minutes more to tell you why I introduced this. But you're going to see why this model can give us the data of inverse localization length. That's what I'm going to talk about.
By the way, this model is on the line or it's on the
On the
line or ring?
that's I'm gonna tell you about later on. Okay, but for now it's suppose it's on a line, okay, infinite line. But I'm going to tell you what I actually did. And in the actual numerical calculation, of course, you can't do an infinite line, right? Okay. But for now, please think that this is an infinite line. And I introduce the preference in one direction. And so if I express it in matrix, it's going to be like this. So here, this lower subdiagonal is always greater than upper subdiagonal. Okay. Now, I found that the spectrum of this this model looks like this. Okay. So I shifted all I changed here this real parameter g. So this is 0, 0.1, and so on. And I shifted them a little bit more so that they don't overlap and mess it up. Okay. Let me see. So let me explain one by one. So here is g equals 0. So this is a Hermitian random model. Okay. If I introduce just small g equals 0.1, so the model is already non-Hermitian, but you can see that still all the eigenvalues are real. And in fact, if we if we compare them in details, the eigenvalues are actually almost identical in the numerical precision. Okay. But then when I further increase g to 0.3, finally I have complex eigenvalues, but only in the middle. And actually this part is again almost identical to here. Okay? And if I increase g further and further, then this complex eigenvalue, the range of the complex eigenvalues expand, and finally here I almost see an ellipse. Okay.
They are on the line. One would expect that they will fill the whole plane somehow.
They are almost on the line. Yes. Okay.
In 1D you can show it.
In 1D, yeah. In 2D and 3D, it's different. Okay.
So
But
that means that you have a critical value of g at which imaginary part appears, or they always exist at any finite g but are extremely small and invisible.
I'm gonna tell you about that. Okay.
Is this picture, is this for one distribution of dx, or is this somehow disordered around?
One sample, only one sample.
Okay.
Yeah.
So
And
the picture may be slightly different if the choices of d along the
right. I'm going to talk about this periodic boundary condition later on, but what I did numerically was put the model on a ring and on 1,000 site with one sample, and so there are actually 1,000 dots on this here. Okay. So so why do I have this kind of spectrum? That's what I'm going to tell you next. And to explain that, I compare this model, this non-Hermitian model, with this Hermitian model. Okay, so here instead of this real parameter, I have pure complex number here. Instead of this, I have pure complex number here. And because of this, so this is Hermitian model, right? And indeed, this is called Peierls substitution, and Peierls proposed to treat vector potential in one-dimensional Tiedemann model in this way. So this theta is actually a vector potential in 1D. But you see, in 1D, if it's on a line, and if you have a uniform vector potential in this way, then it means that there's no magnetic field because there's no rotation. So we should be able to gauge it out, this vector potential, somehow, right? So, and how does it work? It works in this way. So I add the phase into this x side. This is the ket where the particle is on the x side, I add this phase factor, and on this I add this phase factor. Then because of this x plus 1 and x, because of this difference, this phase factor is cancelled, and this phase factor cancelled, and it becomes it goes back to the original 1D Anderson model. Okay, so from this I can tell that this Hamiltonian must have the same spectra as the original Hermitian model without this vector potential. Okay, now so what happens if I do this substitution? If I do substitution, then it goes to a non-Hermitian model. So in the non-Hermitian model, I can do this imaginary gauge transformation, and it should cancel these terms. It appears to cancel this term, but the fact is we have these complex eigenvalues. So indeed, for g equals 0.1, the eigenvalues remain the same, but if we have large enough g, then the spectrum changes. Why the spectrum changes? Because we have to take account of the eigenfunction. Okay, so when I made the gauge transformation to the Hamiltonian, then I also changed the wave function, adding this term. Okay, so and as I said, the localized wave function looks like this, and if I make this transformation, then when g is small than kappa, then the wave function is actually still normalizable. So which means that this gauge transformation is still working, and the resulting wave function is still normalizable. But once g gets greater than kappa, then it becomes unnormalizable, and so we can't use this wave function anymore, and we have to discard this. And indeed, that's when the eigenvalues become complex. So that's what's happening. Let me explain that again in this figure. So suppose we introduce g into this level of 0.1. It doesn't touch this curve. So here, g for all states, g is still smaller than kappa. Okay, so for all states, that imaginary gauge transformation works, and that's why the eigenvalues are changed, and it stays real. Okay, but if I increase g to, for example, 0.4, then I have boundaries, and in this range, g becomes greater than kappa. So for these states, the imaginary vector potential, imaginary gauge transformation doesn't work, while for these states, it still works. Okay, so for these states, because of the imaginary gauge transformation, we can see that the eigenvalues stay real and the same. But for these states, that imaginary gauge transformation collapses and something new happens. And indeed, what happens is that the transition from a real eigenvalue to complex eigenvalues. Okay, so that's why we have this kind of spectra. And so for example, for g equals 0.5, so in this range, we have the condition g is greater than kappa. And in this range, we have the condition g is smaller than kappa, right? So which means that here, g is actually exactly the same as kappa. So this boundary here, so the eigenfunction of this energy originally had the kappa equals to 0.5, right? So that's how I can draw this green I could draw this green curve. Okay, yeah.
So can you go back to the last slide?
Sure.
So in that one, when the spectrum is purely real,
Mhm.
are you saying it's identical to the G for zero spectrum? In other words, is there no motion of eigenvalues? The argument
Well, numerically at least, they are almost identical, and they are actually not completely identical because I'm using a periodic boundary condition. That I'm going to tell you later in a couple of minutes. But in at least in numerical precisions, they are completely identical. Okay.
You can do perturbation theory for very simple G.
Right. Well, yeah, I'm gonna tell you how they can be different. They can be different in exponential to the minus 1,000. Okay.
The size of the system.
The size of the system. Okay. Okay. So then I make two comments, and one is if instead of I've been talking about the random potential problem, but we can also talk about the random hopping problem. So here in this Hamiltonian, hopping element depends on x, okay? And we can choose this as random. Then inverse localization looks like this, and actually it touches 0 here. And this is an exceptional case where we have an extended state even in one dimension. Okay, so because of this, if for this Hamiltonian, if we introduce G, there are complex eigenvalues immediately around here. Okay, so that's one comment, and okay, so the next one is about the periodic boundary condition. So as I said, of course we cannot do numerics of infinite system. So what I actually did was to compute the periodic boundary condition. So it's on a ring actually. Okay, so this periodic boundary condition for a large system actually mimics what I told you before. And let me talk about that. So for G smaller than kappa, this would go really small, and this may be going becomes smaller a little bit slower. But if the system is large enough, then the mismatch from this on this boundary and on this boundary would be very, very exponentially small. So even for a finite system with a periodic boundary condition, if we have this under this in this range, this wave functions can still survive. While in this range, of course, we cannot survive because there is a huge mismatch in here. So indeed, if we don't apply periodic boundary condition, then all eigenvalues stay real, indeed. So we make the periodic boundary condition, and that mimics the infinite normalized wave function and unnormalized wave function. Okay, so in the language of metrics, we have this periodic boundary condition, and if we do that imaginary gauge transformation, we can make all this to the same, but then we have this large element in the boundary, and if eigenfunction has a substantial element here, then something changes. Okay, but if the eigenfunction is localized strongly, then eigenfunction doesn't touch this, and so that's then the imaginary gauge transformation works. Okay, so that's how periodic boundary condition can mimic the argument for the infinite system. Okay, I've been talking about this non-Hermitian Anderson model, and so that's how I obtained these green curves back in '96, and you can see that there are some noises here because I did this only for one sample. So here is some noise, but I could confirm this by doing a transfer matrix method, but I didn't like it as I said, so I didn't do it. And then finally I found another completely independent method to compute this inverse localization length, which I'm going to talk about.
Sorry,
Yeah.
one question. Previously, when you were showing the profile of the modes, this was the rescaled modes, correct?
Which
Over here.
okay.
That you see, so that the modes, so to say, they are decaying faster on the left than on the right. But this is because you are taking. So what you are plotting there is what the E gx times psi of x, or only the psi of x?
Here. Okay, so here this curve I meant g to the minus kappa minus g. Okay, so I can. Is there a chalk?
Chalk on the other side.
Oh, okay. So here, on the right-hand side, I meant something like this, and on the other hand, something like this. Okay. And so in this range, the mismatch is exponentially small. So yeah. So as I said, there is an exponentially small imaginary part, I would guess, for finite g in this range, but it's virtually numerically invisible. Okay.
The larger limit is equal.
Yeah.
Can you just show us the energy curve again?
The energy plan.
This one?
That's it, good.
Yeah.
Oh, I see. So it seems it's not symmetric between the positive imaginary and negative imaginary.
No, it is.
This one? Oh, this one? This one?
Is it symmetric?
Well, actually, I shifted. So actually, this is always real axis.
It should
Yeah.
be
So it's always symmetric, and so it's because the matrix is real matrix. There is a exact symmetry between this and this, and because random potential is stochastic, probabilistic, so there is a probabilistic symmetry. Okay, statistical symmetry. Okay.
Can I ask one more question?
Sure.
The way that you are having your matrix, essentially the off-diagonal elements, they are scaled in an asymmetric manner. So one it is e to the g, and the other is e to the minus g.
Uh-huh.
But if you allow me the freedom to have, let's say, plus minus e to the g, and plus minus e to the minus g.
Good question, and I'm gonna come to the end of my talk. Okay. But. Huh? Reading my mind? Well, but it's a good sign. I mean, people can, and people is following me, right? I hope. So I'm going to talk about this Chebyshev polynomial expansion. It again starts in back in 90s. This Richard Silver is a good friend of mine in Los Alamos. When I was postdoc in Los Alamos, he came up with a very nice method of computing the density of states of Hermitian matrix. Okay, so suppose we have a n by n Hermitian matrix. From now on, I don't have till the end. I have basically a Hermitian. I'm talking about Hermitian matrix in this section. Okay, so this is a Hermitian matrix, and this is by definition the density of states of this Hermitian matrix. And the point is, I want to expand this in terms of some kind of orthogonal polynomial. And it turns out that the Chebyshev polynomial is the best choice. So this is a Chebyshev polynomial of all orders. And the point is, if we can find this expansion coefficient, then we can approximate this density of states quite well. Okay? So how can we find this expansion coefficient? Well, using this orthogonal relation, we can multiply this another Chebyshev polynomial and make the integration, right? So it turns out that this coefficient is given in this form. Okay, that's reasonable. But we can transform this into this form because this is the summation of the delta functions, and then this summation is actually a trace of matrix polynomial, right?
Rescale the matrix so that the spectrum falls between -1 and 1.
Oh yeah, yeah. Okay, so thank you for the reminder. So this Chebyshev polynomial is defined only from -1 to 1. Okay, and so I have to rescale the matrix so that the spectrum falls on from -1 to 1. So it doesn't work for spectrum if that extends from -infinity to infinity. Okay, but for tight bind model, it's from you can always scale down the spectrum from -1 to 1. So that's how I can expand this way. Okay, and then I can find this expansion coefficient in terms of a trace of matrix polynomial, and I can generate this matrix polynomial using the recursive relation of Chebyshev polynomial. So T0 is actually an identity matrix, and T1H is H. So I can generate T2H by multiplying H and H here, okay? And then I can generate T3 by multiplying H and T2, and so on. So every time I multiply the matrix, I can generate the higher order expansion coefficient. Okay, so this Silver's method works. This is the procedure. So I generate higher order matrix polynomials. I take trace and I can find the expansion coefficient. I use this expansion coefficient to int here, and I can find the density of states. But of course, in numerical calculations, you can't sum up to the infinite order. So you at some point you cut off, and because of this cutoff, typically density of states looks like this. Higher order Chebyshev polynomial has a very rapid oscillations. So if you ignore higher order, you see these kind of noise. Okay. So in this kind of expansion of density of states, you typically introduce some kind of smoothing procedure to find a much smoother function. Okay. Now I'm going to the inverse localization length. Now I in a completely different study, I came across with this Fowler's formula, which was indeed a quite old formula, which relates this density of states of this one-dimensional matrix to its inverse localization length. And this relation, is roughly speaking, comes from inspecting the behavior of the element of the Green's function between the zero site and the far away site. So from the definition of the Green's function, I have this formula which is mapped to in this kind of form, while this decays in exponentially in the same way as the wave function. So by identifying this and this, by equating this and this, I can find this kind of formula. So that's found in already in 72. What I did was very simple, of course. So you can see what I did. I inserted this Chebyshev polynomial expansion into here and find the Chebyshev polynomial expansion of this one. And it's simple, but it looks like, as far as I know, nobody has done it. So so that's how I came up with. So this is so I did this kind of integration of the Chebyshev polynomial here, and then I came up with this expansion formula. So now the procedure here is to generate higher order Chebyshev matrix polynomials. The expansion coefficient, that's the same as before. I insert here, and this is the inverse localization length. The only difference is I have now this here, and so actually this expansion converges faster than the expansion of the density of states. So even if I introduce the cutoff, it has this smooth curve. Okay, so that's the red curve. So it looks very reasonable. It looks quite. It works quite well. So and indeed, after almost 20 years, I was able to confirm this green curve by this red curve. So that's why I was so excited when I see this figure. Okay, I still have some minutes, right? So let me just mention the final thing about random sign model, which you asked. So here, so this was done by Joshua and his coworker Tony Z, back in '99. So this is here. This is plus or minus 1. And this is also plus or minus 1. But they are chosen independently randomly. Okay? So here's random. But because they are independently chosen, this is non-Hermitian. So the spectrum is already complex at this stage. You can see. Okay? Now, how the spectrum looks like? Of course, you know, and but how can anybody guess? I'm sure nobody can guess, because it looks like this. So this is 10,000 sites. After 20 years, I was able to do the numerics for 10 times larger matrix. That's why this is 10,000 sites. But it's one sample, and you can see I can argue actually that it's completely symmetric here and here. Okay? And it's also statistically symmetric between along this direction. Okay? But other than that, it has a beautiful feature of this fairly seemingly fractal spectrum. And when we found when we rediscovered this with I discovered this with David Nelson and Ariel Amil on our collaboration during my collaboration, and we called it Mothler. And I understand that nobody outside Japan. Well, David Nelson knew this, and he named that spectrum Mothler, but I understand that nobody else knows this. But this is one of those Japanese monsters in movies. So it's
they're at Comic-Con.
Oh, okay.
Not this meeting.
So you can see these are buildings, so you can see how large this is. Okay, so it's a big moth. Then the point is how. So this is again one-dimensional random model. So we are interested in the inverse localization length of this. Okay, so so to compute that, we introduce this gauge field, imaginary vector field, and so now it's there is a preference to the right. Okay, now this time, can you imagine what happens to this spectrum? No, it looks like this. So it's Godzilla coming and punch a hole in Mothra. Okay, so but more seriously, so this is the contour. So because I added the G to 0.1, this is a contour of inverse localization length that's 0.1. So we can draw a contour line by introducing this imaginary vector potential. Okay. So oops. Wait a sec. Oops. Yeah. Yeah. What? Oops.
It's the control.
Okay. Question? Yeah.
What?
Say it again.
So this one is for some value of G?
This is yeah. So this is this model, the spectrum of this model. So by introducing G here, we can apply the same argument, this G imaginary gauge transformation, and so we can still that imaginary gauge transformation still applies to this. Okay, so and that's how when G when this is for G equals 0.0, but if I apply G to 0.1, then this opens up like this, and so this line, this curve is the contour of kappa equals 0.1. So that's why they become delocalized. And yes.
How about the outer region, the boundaries remain roughly the same?
These remain the same. Yes. Yes. I mean. Say it again.
The middle one is not 45 degrees straight line. Because the outer,
This one.
no, sorry, the outer boundary.
This one. Oh, this curve.
Yes.
Well, I would assume that this is you know better than me. This is really fractal, I guess. Yeah. This is this is supposedly a fractal curve. Okay. If I apply G greater than 0.1, then this becomes wider and wider, and eventually it's like this. Okay. Okay. So that's the end of my talk. Thank you very much for your attention.
Okay, after a lot of questions during the middle of the talk, are there any more? Oh, no. I
Yeah.
never
Very
would
simple
have
question.
expected it.
What is the classical limit of your quantum model?
Classical limit.
Hawking model.
Uh,
It's very heavy. The Hawking particle is very heavy.
Let's see. What do you mean by classical limit?
Well, if it takes a quasi-classical approximation, something like this, so that when h here becomes infinitely small, so that what will be the classical dynamical system that you will obtain?
So let's see. I can. This is in the discretized space, but well, I can write. I can write this kind of Hamiltonian. Okay, so normally this would be e to the like this, but instead of a vector potential, real vector potential, I replace this real vector potential with the imaginary one. So this would be the Hamiltonian, and I guess we could maybe discuss classical dynamics out of this Hamiltonian.
Which version of this problem? Is it quantum
Yeah, if we discretize it, that it looks like this. Okay.
This is in the complex plane.
It's a complex Hamiltonian.
Yeah, this is a so dynamics would be in a complex plane, I think. Yeah.
So you have complex trajectory. Yeah.
So when you are showing the Chebyshev method,
Mhm.
calculate the inverse localization, then does it also work for random hopping? And you have a extended state?
Random hopping. Yeah. So actually, oops. Wait a sec. So actually, let's see where it is. Wait a second. Okay. Oh, here. So this curve I computed from the Chebyshev polynomial. Okay. Yeah.
Okay. Yeah.
Mm-hmm.
Do we have a physical system that can be described by this problem?
Oh. So okay. It goes back to your original question, why I came up with this model, and this model. So you see, there is a mapping of a statistical d plus one dimensional statistical model onto a d dimensional quantum model. There is a mapping between d-dimensional quantum model and d plus one dimensional statistical model. So in the d plus one dimensional statistical model, this particle looks like a string object. So in the statistical mechanical program of d plus one dimensional string object can be mapped to a d-dimensional quantum problem of particles. Okay. So this can be mapped to a two-dimensional statistical model with lines, strings moving in with the external force that's tilted in one direction. And because of this, the world line has to tilt, has a tendency of tilting one direction. That's represented by, oops, this is not the one. That's represented by this right-going preference. And actually, the very original model that we discussed, we had in our mind with David Nelson was the three-dimensional high TC superconductor with the magnetic flux line in it. So it's mapped to a two-dimensional quantum model with this kind of
The world lines are the vortices, pinned vortices.
With this impurities become a pinned vortex, straight columnar defects, while because of the tilted magnetic field, the magnetic flux line tries to tend to tilt, and so in one phase the flux line is trapped by columnar defects, but if it's tilted enough, then it's delocalized, and that's the delocalization transition. And so that happens in 2D, but in 1D, it's in 2D. It's a little bit numerically difficult, so we didn't in 1D, and so in the spectrum. So these actually corresponds to the flux line trapped in a columnar defect, and these corresponds to the delocalized flux line.
I guess it's supposed to be at low temperature.
Yes, it's low temperature. Yes.
Can you just go back to the previous slide?
Of the Hamiltonian?
Yes.
Okay.
I presume that you should be able to introduce a similarity transformation which will hermitize that Hamiltonian, or in other words, construct a metric, and presumably that will become singular precisely at the point where the spectrum starts to show the
Yes, exactly. So So, well, you know, that's what you say about this similarity transformation is exactly this. This is the similarity transformation that brings this Hamiltonian to a Hermitian one. And indeed, that if I apply that similarity transformation, I can make this all to 1, and I can make all this to 1. Okay, but for a finite system on a ring, I have this factor that the gauge is concentrated on one bond, one link. So that's what happens.
Yeah.
One more question.
Yeah.
Your system is non-Hermitian and also non-symmetric. It's non-symmetric.
No,
It-
that's right.
Oh, this Hamiltonian? You mean it's real non-symmetric matrix? Yes,
It means that you are having left and right eigenvectors.
exactly.
Now, when you calculate over here the and because it is non-symmetric, you don't have a specific symmetry between the bra and the cat. So when you calculate over this one here, which
Well, so what happens is I was talking about the right eigenvector, but left eigenvector is exactly the opposite. So the left eigenvector looks like this. Yeah. So and it goes like this at the same time. Yeah, but it's a reasonable question. Yeah.
May I just make one comment
Sure.
concerning the Chebyshev? You have to cut off the sum just technically to put on the
Mhm.
computer, right? So perhaps you can actually improve the quantification by using asymptotic formulas for the Chebyshev, which you can use by the so-called WKB approximation to the recursion relation. Maybe it can help.
Right. I think it's exactly what they did for the density of states, and so that's how they can have a smoother function. But in the case of the inverse localization, I didn't need it. That's
Because
also a
it's,
point because it's
the Lyapunov exponent is self-averaging, has less fluctuations in the emission.
okay. Mhm.
Density of states.
Okay. Yeah.
Short question. When is in the the G is small enough,
Uh-huh.
so there's a mismatch. It's exponentially small.
Yeah.
But there's still mismatch.
There is a
When you
mismatch.
go to the periodic boundary position, are you discarding some good solutions away?
No. So if for example, if I did this in Mathematica, and if I try to find the higher precisions, then I think you'll find a small, very small, tiny imaginary part for this. If you do it for finite system, but it will become smaller and smaller if we expand the matrix larger and larger.
This mismatch will be your numerical precision allowed.
Yeah, yeah, right. So within the double precision of numerical calculation, they are real, and
Phil?
When you expanded the density of states as
Mhm.
a sum of delta functions, you didn't allow for degeneracy.
No, it's if there's a degeneracy, I think it works fine. So this is if there's a
But if the emus repeat,
Uh-huh.
So you sum.
no, but when you do the Chebyshev analysis,
Uh-huh.
how do you take into account the emus that might be degenerate? How do you do the counting?
well,
You use your H.
so the expansion coefficient let's see, expansion coefficient looks like this. So if there's a degeneracy, you simply sum twice. Actually, so if I can translate your question. So you know, for finite matrix, of course, you know, it's the summation of the delta functions. So if I did the summation of higher order Chebyshev polynomials into infinity, if I did that, then you would see spikes, right? And in fact, you don't want to see it because you actually want to see a infinite limit of density of states, and the infinite limit you would expect some smooth curve of density of states. And so this cutoff of the Chebyshev summation actually works in 2 ways. One way is you see you have numerical error, but the other way it actually smooths these spikes. So it's in one way it works in one good way actually. So.
All right, so I think we should take a 2-minute break before we, maybe a 3-minute break.